Hello everybody! I hope everyone's having a wonderful day. So last day I introduced the concept of a B tree. So this is the final main topic we're going to talk about in this class. So remember, I defined last day that a multi-way search tree is called a B tree if the root of T has at least two children and at most D. So it's a little special than all the other internal nodes. So every internal node must have at least the ceiling, or remember, think of this rounding up, D over 2, and at most D children. And lastly, it has this level, the depth property that we talked about with 2-4 trees. So this is a generalization of the 2-4 tree when D is equal to 4. You got to think of D like some arbitrary constant that you can fix, but all the stuff will still work even when D is not a constant. So I'll oftentimes treat it like it's not. However, usually in practice, it may or may not be. So last day I drew out a B tree for you. So for example, here's a B tree of order 5 because it has at most, one of these internal nodes has at most 5. It's this node right here. So if I were to have 6 children, for example, and I wanted to maintain that D is equal to 5, would that violate the B tree definition? Yeah, because D would now no longer be 5, now it would become 6. So I'm going to just assume that whenever I design one of these trees, that in fact is just some number that we ideally want to have. So when I design the tree, I'll just keep in mind what D ideally should be. Okay, so the first thing I need to bring up is the height of a B tree. So I'm not going to prove it here. The proof is rather similar. It's similar to the one that I gave you for a 2-4 tree. You can prove that the height of an arbitrary B tree of given height with the given order D is log base D of n. So we still have the logarithmic height, just now the base is D. Sorry, I was getting excited about this. So the height is in fact going to be still logarithmic. So the big thing I want to point out is that all the algorithms I gave you for 2-4 trees, they're just the exact same for a B tree, just we're going to change things up a little bit. So let me talk about that. So I'm just going to say that, so all the algorithms for B trees are the same as with 2-4 trees, but we're going to need to redefine two things. I need to redefine, for this to work, I need to redefine for you what underflow and overflow are. So a node overflows if it becomes a D+1 node. So, for example, if I were to introduce another record into this node and I wanted to ensure that D was equal to 5, this would violate the properties of my B tree for that given D, and it will overflow. What do you do when you have an overflow? You do splits, right? You do a split operation. Not literal splits. Don't do splits on the ground unless you're really good at that, okay? And lastly, a node underflows if it becomes the ceiling of D over 2 minus 1 node. So how many keys does a D over 2 minus 1 node like this have? Well, it's 1 less than this, right? So remember, this is the number of children. So this comes back to my remove algorithm from the other day. So the underflow occurs when this happens, and whenever we're allowed to do a transfer operation is when we have one, at least one higher than this. So it would have to have at least, it would have to be the ceiling of D over 2 node plus 1, right? Because it would need to be able to borrow 1. Does everybody see that? So that's all we have to do. The algorithms I gave you apply just to B trees as well. That's why I wrote them in a very general way. So let's talk about how you do insertions and removals. So on insertions, on an overflow, remember the muffin top, a split operation will produce 2 nodes. But instead of being a 2-node and a 3-node, it's going to be the floor of D plus 1 over 2 node and a ceiling of D plus 1 over 2 node. So remember, cleaves about the middle, that's the middle. Once I've introduced that one new record in, that was put into the one node for which this occurred, right? Which had D plus 1 children, right? So it just cleaves that in 2. And that's good enough, right? This is going to be big enough so that it doesn't violate the size property we have for B trees. So let's do an example. I'm going to attempt to insert 25 into this B tree of order 5. So just remember, here, D is equal to 5. So I'm going to insert 25 into the tree here. What's the first thing I do? I start up at the root and I work my way down. I try to find the lowest insertion internal node, that V. That's right here, right? I'm going to put 25 in here, so I insert it in. So I insert it in. It gets inserted in. I shuffle everything over. And there we go. So there's 25. Now make sure I don't lose that leaf there. So now I have 25 there. Is this okay? Are we okay with this? Is that going to overflow? Are we having muffin tops? Unfortunately, yeah, we're having a muffin top. This node is too fast, okay? Unfortunately, remember the B tree, just like the 2-4 tree, is very diligent about fitting into its favorite genes, okay? So, just dying here. So what do? What did split say to do? We split about the middle, right? So what did we do? We're going to split right about here, right? So that's about the middle. In fact, this is the middle. So what do? I bring up 25 and I split this into 2 nodes. So let's split that into 2 nodes. 25 goes up to the parent. 25 is here now, gets promoted, up here. On its left will be this node, and on its right will be that node. So I perform the split here, and then what do? I would then go up to, I would check if the node still overflows. I guess I'm getting a little ahead of myself. I go up. That one's okay, right? As long as it has at least 3 children, but no more than 5, we're okay. And we're done. See? Insertion's really easy. Okay, how about removals? On removals, on an underflow, on an underflow, what happens? Well, one of two things happens, a transfer or a fusion. So a transfer operation moves a record from a sibling node with at least the ceiling of d over 2 keys, which would of course imply that it has the ceiling of d over 2 plus 1 children. So it means that when I move over that key from the sibling, remember that's W from last day, this will not cause an underflow at the sibling. Or a fusion operation occurs with its sibling. So keep in mind when I'm talking about the sibling, it's like last day. An adjacent sibling, so one of its at most two siblings, that might be adjacent to it. So one of these two things happens, nothing changes, just the quantity of how many keys might be involved, okay? It's just that now we have to be a bit careful here. So let's do some examples with removals. So I'm going to remove, I'm getting ahead of myself. Let's remove 30 from this tree first. So let's do a bunch of removals, just so I want to make sure you really understand this. Because if you understand how it works with the B tree, you understand how it works with the 2-4 tree. And in many aspects, you really understand the whole game, okay? Because remember, this generalizes over many of the structures we talked about in this course, including the binary search trees. So, that being said, let's remove 30. So what do? We replace 30 with its successor, right? Where's the successor? It is located right here. And the train is very excited about getting that successor, okay? See? Told you. So, I'm going to replace 30 with 32, and I'm going to delete 32. So what happens? I delete its associated record. So what do? So, I noticed a typo in our tree from the other day. This should actually be a 34 right here. My bad. That's bad. I meant to put a 34 here, and it's been there for this whole time. It didn't affect anything, but we'll live with it. So, somewhere in the past, you'll find out this typo from this point, okay? So now I've deleted in that one here. Now I have a 2-node. Are 2 nodes allowed in this B tree of order 5? No. There have to have at least 3 children, which would of course imply that I need to do what? It's underflow. So this underflows right here. So what do? I have a sibling that has more than enough that it can share, because if I remove one of these from here, I end up with just 3 children, right? So I can perform a transfer operation. So I can promote up what? Actually, I'm looking at this now. That's not supposed to be a 32. That's supposed to be a 35. That would explain it. My apologies, everybody. Yeah, that's a 35 here. For some reason I wrote it down as 32. So let me fix that. So now I have 35 here. So let's do the transfer operation. So I bring up 36, I bring down 35. So I end up with 34 here, 35 here, and then 36 is going to go up here. And then I borrow. So just to make sure you know I'm not cheating, this leaf node goes over here and we're done. So notice that this has 3 children. I go up, but do I go up? No, because I did a transfer operation. I don't need to do any more. So there, we're done that removal. So we remove 30. Okay. My apologies for that. For some reason, I don't know how I got away from me. So next, let's remove 55. So, what do we do here? We're going to next need to do what? Where's 55? It's way over here. Well, it's already down here in the lowest insertion point, but notice all these are leaves, so I can just simply just get rid of this, like that. Now, is this okay? Is V okay here? No. I need to do something. There's not enough records here to do well with this. My sibling is also a 3 node, so I cannot borrow one. They need to cooperate together, so I need to perform what kind of operation? A fusion operation. So I'm going to fuse together all of this. Remember, this is W. I'm going to fuse W and V together. I'm going to fuse W and V together. Then, I'm going down 50. 50 is going to go right here. So, am I done? So now I have 5 children here. I go, because remember, fusion, I have to go to the parent and check if that isn't underflowing as well. So it doesn't underflow. So I go up to the parent, and I see that I go up here. Okay, that one's okay at S3. So I think we're okay with that. Let's do one more. I just want to really make sure you get this. Let's do 34. You know where it's supposed to actually be. 34. So let's remove 34. So where's 34? Down here. I perform the removal. 34 is gone. Is this okay? No, it underflows. So what am I supposed to do? Look at my sibling. This is a 3 node, so I cannot just do a transfer operation. I need to do a fusion operation. So I'm going to fuse this with all that together. So I'm going to fuse these together. Then I bring 36 down into my new fused node. So I have 35, 36, 37, and 39 right here. And I have all my leaf nodes. I didn't lose any. Then, what next? I go up. So V is now the parent. Is this one okay? No, it underflows as well. However, notice that my sibling, my direct sibling here, has 4 children, so I can do a transfer operation. So I'm going to do a transfer operation. I'm going to bring 32 down here. 32 comes down. 25 goes up. And then I borrow the child and I bring it over here. And there we go. So we go up here, and now the root has 2 children. We're okay. Remember, the root is the exception in the B tree. And we're done, believe it or not. So those are insertions. There's removals. How long do insertions and removals take in a B tree? How long did they take? So think about it. What were the running times I had last time? I had big O of H times D, right? So remember, for both my operations, for both insertions and removals, we had big O of H times D. But what's H? H is now log base D of N, right? Which is big O of D log base D of N. So if you make d a constant, it's still logarithmic. That's the neat and interesting consequence here. So if you want to let d be arbitrary, where you just kind of pick some value and you have some application that may require that, this is still pretty good. However, normally if d is constant, then this just turns back into log n, right? Does everybody see that? So that concludes talking about the operations on a B tree, believe it or not. So let's switch gears. And now I want to talk a little bit more about why you'd want a B tree. Because you might say, Dan, earlier on in the course, you talked a lot about AVL trees. You talked about all these different things. Why the heck would we want to implement something this complicated looking? Although all the principles somehow look very similar. So why would you want to have a B tree? So just remember, a B tree is a generalization of a 2-4 tree, but in turn, that is also a generalization of a binary search tree. So why would you want this giant overcompassing structure that can capture so many other of these tree-like structures? So why a B tree? Let's talk about that. So why B trees? Heck, why is it even called a B tree? I guess we'll find out. At least one speculated reason why they're called B trees. So the big thing I want to point out to you is that computers have a memory hierarchy. So I should mention that this hierarchy is where each level varies in size and distance from the CPU, or the central processing unit. So the big thing I want you to keep in mind, and this is very much true with general use computers, is we have the notion of a memory hierarchy, which I'm going to draw now. So here's a picture that I want you to remember, because this is a very important picture, and it creeps into systems, and it's something you have to keep in mind when you think about how you access data on a computer. So this is very much both a thing of interest for somebody who's interested in data structures, but it may also be of interest if you're interested in how data structures would connect to other topics like databases or computer systems. But it's generally things you need to be aware of when you talk about a computer itself. So we're kind of escaping the realms of pure, very, very pure discussions of algorithms here. So we're talking about an actual computer. So we have the CPU. Now there's two main kinds of memory in the memory hierarchy. There's volatile memory and there's persistent memory. These are your two main kinds. So the volatile memory, this is your working memory. If your computer turns off, this goes away, okay? So this is being used temporarily. This is where your data after, say, on your hard drive, or if you have an external connection, like a network connection, this would be your so-called persistence or persistent memory. So there's these two main kinds of memory. So the closest of those to the CPU are the registers. So these are internal registers that usually the CPU directly communicates with. Sometimes they're directly on the chip, sometimes they may not necessarily be. Typically, it can be. So as I go down, the further away we're getting from the CPU, the larger the memory is going to get because it is cheaper to produce said memory. So I don't promise these to look to scale because I only have so much space on the board here. Now, beyond the registers are the caches. Your computer may have multiple caches or just one, and each one is given a level. So you might be familiar with like L1, L2, L3 caches. This is in direct discussion of this picture. So you have different caches or just a single cache. So whenever an access occurs from a register, it'll appeal to the cache. If it's not there, it'll go seeking further down. So this is to boost performance oftentimes in a system. It could be quite considerably important because of notions such as temporal locality. So usually when you access something in memory, sometimes you oftentimes access things more than once or from an adjacent part of memory. So oftentimes caches like this really boost performance when you have things like this, okay? So this is not a systems topic by any odd means that I'm discussing. I'm just keeping things very high level. If you're interested more in this kind of stuff, take a systems course. Talk about computer architecture or computer systems. Now below that is the main memory. Now it's considerably bigger than the cache, but I only have so much space here. So this would be where your RAM is. Like if you're using your RAM, this is the main memory I'm talking about. So this is sometimes called the internal memory. So this is where all your working programs, when you're doing operations with a working program, they're loaded into the main memory, and then accesses are occurring between the main memory and the external memory when it does fetches. So what happens is it goes from here all the way through here, and as we're doing these things, you're going to find out that the performance will get better and better the closer you get to the CPU in terms of performance on the actual machine. Now, lastly, we have the persistent memory. So this is your external memory. So this is, for example, like a hard disk. This is like your hard drive. So this is not the whole picture. I got to put the two biggest pieces of this in. So as you go down this hierarchy, think that the amount or size of things gets bigger. So, however, as you go towards the CPU, you can guess what happens performance-wise. It's faster. So naturally, you want to take advantage of having it so that you can take advantage of all this volatile memory and not make so many requests out to the persistent memory, because this is, in terms of magnitudes, considerably higher to seek memory allocations or fetches from persistent memory or your external memory than over here in the working memory that you're having here, your volatile memory. Does everybody see that? So this is the memory hierarchy picture I want to have in your head when we think about this. So that's going to be the big picture. So that's the memory hierarchy. So now what are we going to do with this? I want to talk about how this all comes together with the B tree. I don't want to make too many concrete statements involving the memory hierarchy because obviously hardware changes. However, this general structure has been rather consistent for many, many years. So we're going to consider the problem of maintaining a data structure that we have the following property, where external memory is divided into blocks called disk blocks. And to obtain data on request of a disk block, requires its transfer between external memory and main memory. So these transfers are called disk transfers. So a single one is called a disk transfer. You might colloquially actually know this term in many ways. It's called I/O. So what's our goal? So I want to be able to update this data structure. So I want to be able to request information from the data structure and also perform updates on it. And it's stored in external memory. So I should be able to grab disk blocks that contain parts of my data structure and do manipulations with it. So whether it be updating parts of it and then saving it later, or performing and requesting information on it. So here's the problem. Minimize the number of disk transfers needed to update needed to update our collection of data. Okay, so that's the problem. So we're going to try to minimize the number of these I/O or disk transfer requests. Why? Remember, everything down here is really slow, especially if we talk about like a hard disk. Hard disks are requiring physical medium to spin and request, which is magnitudes slower, like I mean many magnitudes slower than say directly accessing from a register or the cache. So if we can minimize that, the performance on an actual machine might be considerably better. So does everybody understand the game plan? Now, I like to make my discussions of algorithms and data structures quite practical and quite realistic, so I'm going to give you a realistic example of the kinds of magnitudes I'm talking about. Just so you can understand that we're still talking about things that are not very, these are not abstract in the sense that they are useless. They are building blocks of many of the things that run in a system when we're talking about an actual computer system. We're also talking about things that are of also theoretical interest, that a lot of work has gone to building on top of concepts like this. So we're talking about a combination of both theory and practice. So I think that that's the most ideal thing to finish things with in this course. So we're going to suppose that we have a collection of 10 to the power of 10 records. So just for context, what 10 to the 10 is, if you can't count in scientific notation very quickly, that is 10 billion. So I have 10 to the 10 records. So what I want to do first is consider the situation where I were to take an AVL tree and try to do exactly this with it. So I'm going to assume for simplicity that each one of my nodes can be stored in one of these disk blocks. You'll see later it doesn't make much of a big difference, However, in terms of practice, if it does not fit inside of a disk block, you would require multiple requests to read the entire node of your tree. So the whole idea is that we need to be able to read a node in the tree so we can interpret and update any information, or seek out more information so we can learn more about the tree. Does everybody understand that? So the idea is that we want to be able to take advantage of these disk transfers as much as possible. So let's first consider an AVL tree. So let's try assuming where. So we're going to just assume, this is for charitable sake too. I'm just going to assume that data of a node, so I'm talking about the entire node, by the way. So I'm talking about I guess I'll write it down here for everybody. So I'm talking about, let me be precise here. So I'm talking about the references for the node, the data in each one of the records. So an AVL tree is just one. So I'm talking about the whole thing. This is like the whole node. So the references associated, so like your left and right, and data, and the key, all that's in the node. So this is me storing all of that. So fits in a block. I'm going to just assume that it can fit in the block, just to be charitable. Now, if it does not, like I said, multiple disk requests are going, number of these disk transfers are going to be needed, proportional to the size of it. So, what do? Okay, well, let's think about it. If each time I request a part of the tree, where do I start? So let me draw out a picture. So I have my AVL tree, so imagine I have an AVL tree. I don't know what the tree exactly looks like. It might look something like this. Just for simplicity, I'll just draw it like this. So I perform some sort of disk access. Now, it might give me multiple parts of the tree. So it might give me, say, I don't know, like a couple of nodes. So I'm just going to assume it fits in a block, but it might give me multiple nodes in that storage. So each time I do one of these, I'm going to be able to have the information to interpret the node and perform the next operation. So, for example, if I want to request or find where a node, like I want to get a piece of data associated with a key in the tree, what would I need to do? I would need to know everything about that node. So I would load up this node, I would get the left and the right as part of that the disk transfer. And I might get multiple parts of the tree in these requests as I'm exploring down the tree. The point being is that I might get disk access that occur on fetch parts of the tree. Does everybody understand that? So if I wanted to be extremely specific, I would just load one node in as each time I load something. Does everybody get that? So if we want to find a record, what does that relate to, actually? Well, I need to access each one of these in the worst case, right? I have to access this node. And say, for example, the node's right here that has my record in it. I would need to access the disk. I would need a disk transfer for this, disk transfer for that at worst, and another disk transfer for that one, right? So I want you to observe that the number of disk transfers, or accesses depends on the height of the tree. So it depends on the height of the tree. So, because I could request one way down here, or it may not even exist. So I need to be able to tell you when it doesn't exist, right? Which will currently go into a leaf, which at worst could be proportional to the height. So, what's the height of an AVL tree? So what's the height of an AVL tree? Well, we know that it's big O of log base 2 of n. So if I wanted to estimate how many disk accesses I'm going to need, well, I'm just going to take my magnitude here. So to search for some key k takes log base 2 of 10 to the power of 10, which I need to mention is about 33 disk accesses. So notice I just put in the number of records, right? Just 10 to the power of 10, which is roughly 33. So it's going to be about 33 disk accesses. If that drive is really slow, this could be not good, right? It's not ideal. So I'm going to say this could be expensive to do. So remember, when we're doing this, I'm only caring about how many disk accesses are required, which happens once per node in the worst case, right? So I don't really care about the running time of the get operation, or the insertion, or the removal. I just care about how long it takes me to get to that node, because it requires me to do disk accesses, right? So I'm just going to care about this finding business. So what about when we have a B tree? What happens when we have a B tree? So let me show you. Okay, so I had an ABL tree before, now let's consider the B tree. Now, this is why that D being allowed to be picked is very valuable for us. But we're just going to pick D so that the data required to store a node in a node of a tree fits in a block. To be more precise, what you would do is you would let D be big O of capital B, where capital D is the number of elements in a block. So as long as you make sure that D is sufficient so that it fits in the block, you're okay. So when we have this in our play, I want to show you what we could do. So I'm going to draw out a B tree. I'm going to assume that I could fit it so that D is equal to 10 cubed. So the order of this tree is 10 cubed. So what would a B tree like that look like? If it's 10 cubed, that's 1,000. So how many keys does it have? It always has one less than the number of children. So I have key 1, key 2, all the way up to the 999th key. And each one of these will have some children. Remember, it's a B tree. So if there's a leaf node on one of these, it's going to be across all of them. So there might be more down this way. I don't care too much about that at the moment. Also could be, there's plenty going on in between here. So what I'm going to do is I'm going to make sure that this node, all the information, so remember the children and each one of the records that fits in here. So how much data that's going to require, that is going to be sufficiently how big I need to make sure that D, when it comes to matching up with B. So just remember, each node here will have at most 1,000 children per node, and there's going to be 999 keys and possibly some data. The point is that we need some way of indexing things. I'm not going to talk about that in too much detail, but the point is that I could fit this into a data block, and I can fit all of these into data blocks. What happens? What happens? I'm going to use the same observation here. It fits. Each of these fit. But the problem now that you should observe is that that one was kind of like the worst case scenario that we've seen in our proof involving the 2-4 trees, right? It was a binary search tree. But now we can make our trees more bushy. They're more bushy like this. So meaning that they're going to be potentially more shallow. So when I do disk accesses, now I just read this whole node in and all the information, and I can retrieve the next node along each path after I do each one of my binary search modifications, right? Where I just kind of go through each one of those, and I can select out and load up the next one through a disk transfer. So let's look at the height again. So what's the height again of a B tree? The height is big O of what? Log base D of n, right? So that's the height. So what is the number of disk accesses then? How many are there going to be at worst? How many are going to happen roughly? Well, it's going to be approximately log base 1,000 of 10 to the power of 10, which this I'm going to just leave as an exercise if you want to calculate that up yourself. But I calculated it out, it's 3. So you'd be approximately 3 disk accesses. Now, I don't need to really say a whole lot, but I want you to look at these two numbers, 33 versus 3. Which one seems more suitable for this external memory concern we have here? The B tree. The B tree is wildly better. So this is why you would consider a B tree. Why would you want this generalized structure? It's because it's natural for disk transfers and transferring of blocks. So do you see where maybe some people would suspect this B might relate to? So notice that I use B here. It might be for block, it might be for one of the names of the creator. I don't know, actually, I'm not sure of how many people even know what the B stands for. I'm not even sure. Maybe you can tell me. The point is that this is one speculated reason why it's called a B tree. B for block. That's one way you can think about the B tree. So the more you, I'm pretty sure the creator, paraphrasing one of the designers of this, the more you learn about the B tree, the more you find the reason why it's called what it is. Okay, so now you see that this actually belongs to one of the wider, like the very, very small classic clubs where the B tree is one of the best when it comes to maintaining data structures in external memory. So that brings me to a theorem. So I'm going to state a theorem, and then I'm going to give you what is kind of like a neat consequence of this. So this is the final theorem of the main topics of this course. So I've spelled out everything here for you. Okay. So, theorem. So here's the theorem. Let B denote the number of elements that fit into a block. A B tree. You see how B now has a meaning here? A B tree with n records, performs big big O of log base B of n disk accesses for search and update operations. Search and operations, and uses, so I got to talk a little bit about the space here, and uses big O of n over b blocks, where b is the size of the block. So I'm being deliberately redundant because I gave you B up here, and I just want to mention B here just to emphasize that I'm talking about number of elements, I'm really talking about the size of the block. So these are just two different ways of saying the same thing. If you don't like this, you can just get rid of this if you want. Okay? So, that's quite a powerful result if you think about it. So you might ask, Dan, why would we care about B trees even after this interesting but powerful theorem? Well, the bedrock for these structures tend to be more specialized. So beyond the B tree are so-called B plus trees. So B plus trees are pretty standard and commonly appear in things like file systems. So oftentimes used for indexing. So they appear in things like file systems. So not every file system uses this, but there are a lot of them that do. And likewise, you can also think of database management systems. I'm not going to talk about what a B plus tree is. So in particular, I'm talking about relational database management systems here. So something you'd learn in like a database course. So the B plus tree is a specialization of the B tree. But yeah, the structure is pretty broad in general. So, that being said, we've started this course really at some more basic things. What an algorithm is, what a data structure is. We talked about how we analyze algorithms. We worked our way up through many different common and what I would consider fundamental data structures. And we worked all the way up to data structures that describe things like some of the things that pop up in things like file systems. So, that being said, we've really come a long way in this class, and I want to say thank you very much for taking this little journey with me. So I want to say thank you very much. It was a pleasure to be your professor, and I hope the best for you. So I want to say thank you very much, and have yourself a beautiful day.